Okay, so today we're gonna go over lecture number 8, where we'll talk about harmonic excitation for damped systems. And we're gonna learn two very important concepts today. The first one is called frequency response. The second one is called Bode plot. And in the very beginning of this class, I said for a vibration system, you can usually analyze it in two different domains. One is the time domain, the other one is the frequency domain. And then over in this lecture, we're gonna learn why the frequency domain is that important. So it's a warning at the beginning. So you're gonna see a lot of math today. So just don't panic. If you cannot fully understand the mathematical derivation, so make sure at least you understand the key conclusions. All right. So let me start a new document. So for undamped system, let's write it out. Okay, so you have MCK for an undamped system. That's something we learned in previous lectures, lecture 3. You have a damper, you have a spring, you have a mass. So MCK, these three defines your damped vibration system. All right, so previously we talked about this kind of excitation. So no force on the right-hand side, or no force is applied to the mass, but we already know the initial position and initial velocity, right? So we call these free vibration. But in this class, your right-hand side is changed. So we are actually having an additional term, which is a force. Let's name it as F naught. Oops. Man, I think something is wrong with my iPad. Give me a second. Let me switch a screen. All right, I'm back. Sorry about interruption. I believe something's wrong with the new iOS system. Yes, I believe somebody warned me that I shouldn't upgrade to iOS 14 because that gives the Zoom file sharing some issues. But there's no way I can go back. So sorry about that. Let me repeat what we got. We have a damped system. So it actually have two inputs. The first input is no force, but we know the initial conditions. The second one is actually a sinusoidal force, or in this case, you can put cosine omega t. All right. So previously we said on the left-hand side, or when you have a mass spring damper, because all the coefficients are linear, your M, CK, they're constants. So that means you have a linear system. So if you have a linear system, you can always use superposition. So you have input number 1. That's your input 1. And then you have your input number 2. So what you can do is you can solve. So what you can do is you can actually solve these subsystems individually. And for input 1, we call the solution as XH. So this H stands for homogeneous. If you remember your ODE class, that's the homogeneous solution of your equation. And then for damped system, we actually want to normalize it so we can simplify the discussion. So we just normalize everything by m. The new equation becomes 2 omega n zeta x dot plus omega n square x equals to small f naught cosine omega t. We call this f naught as mass normalized force. So it's the actual force amplitude divided by the mass. All right. So previously we already learned that the homogeneous solution actually have 3 different terms, or 3 different formats. So the first one is A times sine omega t plus 5. This is the underdamped condition. Oh, sorry, I think I forgot the exponential term. A e minus zeta omega n t. So that's your underdamped condition. And then you also have critically damped and overdamped. So I'm not going to write it down here because in this class we're going to focus on the first condition only. But then all the this method can be applied to other 2 conditions as well. So the way you determine which equation to use is based on your zeta value. If your zeta is smaller than 1, that's what we have in the first case. We call these underdamped. All right. So if you look at these equations, there are 2 things to be determined. One is the amplitude, A. The second term is the 5. And actually, I forget one thing. This omega is not the driving frequency. It's actually the damped omega d. So you have A and phi. They are unknowns. But then this is to be determined by x naught and v naught. So these 2 are related to your initial conditions. All right, so that's for your input number 1. So let's then solve this input number 2. So we call these XPT, is similar to what we learned in the previous lecture. So the P stands for particular. So XPT is one solution of this ODE. And then we don't know how it looks like yet, but we can make some assumptions, right? It's like, I really like the swing example. Assuming that this force is somebody pushing, like assuming the MCK system is a swing, and then this force is somebody pushing the swing. So the vibration of your system eventually will be determined by how you push the system, right? So if you push it in a sinusoidal wave, then your response would also be a sinusoidal wave. And then the frequency will be the same, but then you're going to expect some phase difference because of the damping, because the external force have to do extra work to counteract the energy dissipated by the damper. So that's why your system response won't be immediate. It's not like the undamped system when you push it and then your system immediately responds to the push. But because of the damper, your system takes some time to respond. So that's why you have a phase, or I already used phi, so let's use theta here. Okay. And there is another amplitude. We can name it as big X. So that's going to be your response. And then again, we have two things to be determined. We don't know the amplitude. We don't know the phase here. Okay, so how can we find these two phase, two unknowns? So we already know that your XPT is a solution of x double dot plus 2 omega n zeta x dot plus omega n squared x equals to f naught cosine omega t. All right. So to simplify our discussion, I'm going to play a trick here. So the trick is we want to replace the right-hand side by using Euler's equation. So we assume the right-hand side is f naught ej omega t. Remember that ej omega t is cosine omega t plus j sine omega t. That means your cosine omega t excitation is the real part of that exponential equation, right? So the trick here is you convert this blue equation to the black one, and you're going to write it as x double dot plus 2 omega n zeta x dot plus omega n squared x equals to f naught ej omega t. So you already know that your excitation is the real part of this. So finally your xp is the real part of x, right? Because the imaginary part corresponds to sine omega t. Let's write it out, and then you're going to know what I mean. So we already know that your xp is some kind of harmonic. So if it's your xpt is a harmonic response, so you can write your xpt as something constant c to be determined, e j omega t plus phi, right? We know from the first step here, we know that your force response is going to be a harmonic excitation as well. So in order to define harmonic excitation, you need to use amplitude, frequency, and phase, 3 parameters. And we already know the frequency should be the same as your excitation. So that's why it should be omega there. So that means we need to find your C and, oh, I just really like the variable phi. In this case, let's use theta. We need to find C and theta. So let's do another trick. Because your omega t is time dependent, but your theta is actually a constant, you can move your theta in front and then keep your ej omega t in the end. You just split the term over there. And then the 2 in front, it forms a new variable. We can name it a C start. So your C here is a real number, but then your C star becomes a complex number, right? So in this case, instead of finding C and theta, you just need to find a single value theta star. So that simplifies our discussion. And this becomes C star ej omega t. And then we know that your xp is a function, is a solution for this original black equation. Then we plug everything back. Your xp double dot is minus omega squared C start ej omega t. Your x dot p is omega j C start ej omega t. And then you plug everything back. You have omega n squared minus omega squared times C star ej omega t. And then the imaginary part is 2 omega n zeta omega c star j e j omega t. That equals to f naught e j omega t. And then these equations should be true for every time t. So you can find out your e j omega t. This is your common term, right? Need more space. Insert. All right. So once you cancel it out, you can move things around and find your C star value. Your C star is just F naught divided by omega n squared minus omega squared plus 2 omega n omega zeta j. So as you can see here, your C star has a j in it, so that's why your C star is a complex number. Remember that our xp is C star times ej omega t. And then let's write a C star. We know it's a complex number, so we can write it as the real part plus the imaginary part times j, right? So let's replace it by C real plus C imaginary times j. And then according to Euler's equation, ej omega theta is cosine omega t plus sine omega t j. And then you can express this out. You would have your real part is CR cosine omega t minus CI sine omega t plus CI cosine omega t plus CR sine omega t. That's your imaginary part. So that's your XP. That's your particular solution when your excitation is F naught. Okay, let me write it down. So these XP is the solution when right-hand side equals to F naught EJ omega t. Okay? But remember, on the right-hand side, we only have the real part of these, right? We only have the real part, which is F naught cosine omega t. So that means equivalently, we only need the real part of XP. Because the right-hand side, the force is cosine, is only the real part of these EJ omega t. So your solution is only the real part as well. So that's CR cosine omega t minus CI sine omega t. So that's your solution. So there's another case when your right-hand side is F naught sine omega t. Instead of a cosine function, if you have a sinusoidal excitation, that means this excitation is the imaginary part of this exponential term. So in this case, you need to pick out the imaginary XP, which is CI cosine omega t plus CR sine omega t. So there are two conditions. If it's cosine wave, your particular solution is a black one. If it's sine wave, then you get the red solution. All right, so then eventually we have your solution, xt equals to xht plus xpt, right? Because it's a linear system, you can use superposition, just lump the two solutions together. And then let's go back to the original solution. We already know that, so everything in XP is determined. So remember, in the final solution, we still have the amplitude A and the amplitude phi to be determined. So you have to plug in your initial conditions and then find your A and phi in the end. But one thing I would like to point it out is, if you remember the plots of this XH, write it down. You have your XHT, the homogeneous solution part. So there are three conditions. The first condition is something like this. That's the underdamped condition. Or I should directly write zeta smaller than 1. The second condition is something like this. That's either zeta equal to 1 or greater than 1. So you have no X oscillation. So no matter which case, eventually your XHT becomes 0 when time approaches infinity, right? So that means your homogeneous solution eventually dies out. Or we can say, when time approaches infinity, your xt eventually becomes xpt, because the first term homogeneous solution is gone. So then we have to understand two concepts. The first one is called transient state. The second one is called steady state. The transient state is when let's talk about the steady state first. That's easier. Your steady state is directly xpt. So that means when your homogeneous solution is gone, how does your response look like? That's your steady state. And your transient state is just the rest. When the XH still exists, that state is called transient state, right? So steady state is something we target in frequency domain. I can give you an example. So after class, I post a MATLAB file online. You can check how these solutions look like in time domain. That's your solution xt equals to xht plus xpt. So it looks like something like this. So as you can see here at the beginning, when the time is small, your system it's not a purely sinusoidal. You're going to see some oscillation there, some like change there. So we call these transient. And then after that, you're going to see a single oscillation. This is called steady state. And then it will never change over time. So it's going to repeat that shape forever. So in most of the time, for example, if you buy a sensor, most of the sensors, they just detect the steady state. Like if you buy a force sensor, accelerometer, so that's going to give you steady state. So in most of the designs, you actually want the transient state to die out as fast as possible. Then my question is, how can you make sure your transient state is short? How can you reduce the transient state time? Any thoughts? Let's name these time period as TTR. How can you reduce the value of TTR for a system?
Well, I mean, technically, wouldn't if you could if you increase the stiffness of this like a spring or increase the degree of dampening, couldn't that make it so the system's like dies out faster?
Let me simplify my question. I think that's actually a pretty open-ended question. Perhaps that's for the final project. But right now, let me give you 3 conditions. Smaller than 1, oops, equal to 1, and then greater than 1. Condition A, B, and C. So which condition you will choose to reduce the TTR? A, B, or C?
B, right?
B. So this question can be tricky. Personally, I think A is the right solution because then we have to go back to these plot. Let's go to these plot, the first one. As I said, your homogeneous solution or your transient state is associated with free vibration, right? If you want the transient state to be as short as possible, that means you want your transient state, you want your homogeneous solution or your free vibration to die out as soon as possible. So first of all, you definitely don't want zeta greater than 1 because in that case, your system is really slow in response. So that curve actually takes a very long time to die out. So you don't want that. And zeta equal to 1 is okay. So you won't get any overshoot. So that means your transient state would be something like this. But then if your damping is so small, then your transient state and your initial condition is not fully 0, then you're going to see a crazy something like this in your transient state, and eventually it becomes stable. But so if you pick underdamped condition, then you might have a very crazy transient state, but then you might also have very short transient state. So that means the first one is you get short TTR, but my crazy transient. So here, the condition B is you get like a reasonable transient state period, but then you will never see overshoot. So your system will be reasonable. It won't be like unpredictable in certain case. Okay, so that's it. The other question is, as I said, most of the sensors, they actually prefer steady state response. So how can you calculate steady state response in real life? So we already mentioned one way here. You can solve for your xt and then find the time plot, and then you check your plot and you find out the time, the transition time when your signal no longer changes. So that means you can find like choice 1, you can find steady state in time domain. So what you do is you just calculate, you either calculate or measure your time domain response and then check xt plot, like find when xc no longer changes. In other words, you're going to see a single sinusoidal oscillation, and then at that time you can pick the amplitude and phase shift of that excitation. You get your transient, you get your steady state. But there are problems for this method. It needs a long time. For example, if you have an overdamped system, you might take, sometimes for some extreme cases, it might take days to get a steady state. Actually, there is one example in MATLAB right now. We're printing a material on a very soft substrate. It's like a very thin polymer, less than 5 microns, or sorry, 5,000 or something. It's really, really flexible. If you bend it, build a very tiny stress in this film, it takes a very long time for the polymer to return to a relaxed state. So it actually takes 2 days or more to reach the steady state. So that means sometimes that method is not measuring the time domain response. It's not the best idea to find your steady state. So that's why the choice number 2 is important. So we find it in frequency. Oh, I forgot time domain. We find it in frequency domain. So what does that mean? In order to do that, we have to go back to our XP again. Your XP is, let's assume, to simplify our discussion, let's assume F naught cosine omega t, a cosine excitation. Your XP will be only would be the black solution is CR cosine omega t minus C imaginary sine omega t. And then what is the CR and CI? CR and CI, they're just real parts and imaginary part of this complex C star. Okay. So I'm not sure if you remember the math relationship or not, but I'm going to write it out. So once you have a constant multiply cosine and constant multiply sine, what you can do is you can merge it to create a single cosine wave. So the coefficient becomes the square root of the two coefficients, and then plus theta. And then you can define a theta angle here. That's how you create these. If you don't remember that, you can always draw the circle. Oops. This is your theta angle. And then this is your CR cosine theta. This is your CI sine theta. So that's why CR cosine theta, well, perhaps not. It's just even more confusing. So yeah, so that's, just remember the relationship. You can actually merge two cosines, summation of two cosines into a single sine. And then let's compare these. So let's look at the first term. So the first term here, CR, the two square roots, is just the absolute value of your C star, right? Make sense? Because the real part square plus imaginary part square take the square root. That's just the length of a complex number. And then let's look at how the theta look like. Your theta, your tangent theta, should equals to CI over CR. And then in order to find your theta angle, you just need to find the angle of your complex number C star. All right? So remember that your XP, we have to go back to the very beginning. Your XP is X times cosine omega t plus theta. Okay? So that means this equals to X, big X cosine omega t plus theta. So that's your steady state response. And then your steady state, as I said, is a harmonic excitation, or is a harmonic response. So it has both amplitude and phase. So for the amplitude, your amplitude, big X, is just the magnitude of this complex number. And then your theta is just the angle of this complex number. All right, so that's how you find your steady state. If you want, you can add one more condition. Your omega is just your excitation omega. So one more thing. I think in order to calculate the amplitude, that should be relatively easy. Mathematically, just take the square root of the real and imaginary part. In MATLAB, what you can do is, if you have a complex number C star, in order to find your X, you just use ABS, absolute C star. In order to find the angle theta, you use, I think you can use angle, C star, or you can use tangent invert, imagine C star over real C star. So either way should work. So that's how you do it in MATLAB. If you want to calculate these by hand, if we actually learned these in my own ME 380 class. So if you didn't take my 380, I'm going to explain this again. So your C star is A1 plus B1J, and A2 becomes B2J. And then A1, A2, B1, B2, they're all real numbers. So the magnitude of a complex number in this format is and then the angle of these complex number is tangent invert B1 A1 minus tangent invert B2 A2. If you want to calculate by hand, that's what you have. So that's how we find steady state. So eventually your steady state is related to a complex number C. And then let's go back to this C, where the C is. Your C is something like this. Your C depends on your damping coefficient, your omega n, that's your system parameter. It also depends on omega, like how you excite your system, and it depends on the magnitude of your force, F naught. But it has nothing to do with initial conditions. Your C star won't be changed no matter how you apply your initial condition. All right. So any questions about these steady state? If you want, I can actually write out what was the x and theta we have.
I was gonna say,
So, yep.
I'm kind of having a hard time keeping up because is this supposed to, I'm looking at like the lecture notes that were like that you upload as a PDF,
Mhm.
and like some of them, it doesn't seem to, it has like complex numbers in it, or it's
Mhm.
referencing a complex number, but I'm not seeing a lot of the same equations that you have for your particular solutions and whatnot.
Yeah, so that's what I said like during at the beginning of this class. So here I would like to explain the mathematical background, but if you just want to like prepare for the class or for the exam, then I already post the key conclusions in the lecture. So the I should put it
Okay,
in.
that makes sense. So the
Mhm.
lectures gonna be including the conclusions. Okay.
Yep.
Okay, so we're
So that's
getting
the conclusion part. That's all you need to take to your class to your exam.
okay, that makes sense. I was just trying to connect them a little bit. That makes sense.
Hmm. But
Okay.
then how we get these equations, then you have to go back to the lecture notes I just put there. I'm going to post these online as well.
All
So you
right,
can
thank
see
you.
the math behind it.
That's
Yep.
helpful. I like understanding the math behind it, so I was like trying to see because the conclusions are a little different, at least between this and the lecture notes. So that's what I was looking at.
It's slightly different because in the textbook they use, let me see, where is it? They use a minus theta. They use a minus theta in textbook. But I like to use positive theta. Then you get a negative phase lag. That's actually more common in practice.
Oh,
So
okay, that
the
makes
phase you might see a sign difference, but the amplitude will be the same. It's more common to see a negative theta. Yes, that's most of the time. Actually in my own life, I never see a positive theta. That's not the right way to define theta. So I don't know why they put a negative. All right. So we learned all of these C star. We learned the amplitude. We learned the phase. So why that is important. The, the fundamental question is like, why we have to do this. So I'm going to ask you one question, then you will know. So if you have let's say that's an example. If you have a mass spring damper system, that's your model. And then you apply the force F naught cosine omega t on top. And then you can assume this system is a desk. You have your tabletop. That's a table. And then you have 4 legs, right? If you want, you can also add a dashboard somewhere. But let's assume this is your table, it's sitting on a floor. Somebody is dancing on this table or jumping on the table. All right, so this guy is jumping in a different frequency. Sometimes he's jumping really fast, sometimes he's really slow jumping. All right, you want to design your table the legs of your table so that it will never break, no matter how this guy jumps. You see the question? So what if you have a practical question like this? Somebody jump on the table, you want to design a table like, okay, then we can convert this question into, we can simplify this problem into a lambda parameter model here. So your K is the leg, and then that's your dashboard, and then your tabletop, and your tabletop has a mass M, and then somebody jumping, the jumping force is going to be the cosine excitation. That's just a simplified version for this problem. So we ignore transient state. We only care about steady state. Like we assume transient state is small. So that means your damping might be really large. So once this person jumps, you're not going to see a huge acceleration at the beginning. So then you can use a steady state to design the problem. So because we don't know how this guy jumps, so that means your omega is varying, right? When we design these table lags, we want to make sure no matter what omega we apply, the force, the material is able to stand the force. So this force experienced by all lags, let's name it as F output, equals to K times X. Let's assume this is your X. That's Kx, right? Because we assume that your table lag is like a rod. So I think in lecture 4, we assume that the rod can be simplified into a spring, which is your K in your lambda parameter model. And then the force experienced by the lag, so this is your lags, it's just K times X, the spring coefficient times the deformation. All right. We want to find out F out as a function of omega, right? We want to know what's this force look like for all these omega excitations, and we need to design the lag such that they survive the maximum F out omega, right? Make sense? So let's look at this problem. We know everything. We know this F out is in steady state. We already know that. Okay. So let's write it out. So your F out is going to be the spring constant times X, and then your X is only steady state. Because we only care about the maximum value, so that's why we only, let's say that's your max. So that can be simplified as K times the big X, right? This big X is the amplitude of your XP. So you would have your K times what these big X look like. Your big X is the amplitude for your C star. You can actually go back and copy and paste omega minus omega n plus 2 omega n omega zeta square. So I skip these in this document. You can go back to lecture 8. I already have the equation there. Your equation is for X star. Your big X is a function of F naught, omega, and omega n, and also zeta. So how should we design the system? So as here we know that if you look at this equation, we know that your K, your omega n, your zeta, they're all system parameters. And then your F naught and omega, they're inputs. Or a varying. So these two is determined by the person on the table. So then you can design a system. What do? You can create a 3D plot, right? In one case, so on one axis, you have your x naught. On this axis, you have your omega. And then on the right axis, you have your f out. Eventually, you're going to find a 2D surface, and then you can pick the peak value to design your table. And let's simplify the discussion. So we can do the discussion in 2D. Let's simplify it as f naught is also constant. So in this case, f naught is constant, so then you don't need 3 axes. You just need 2 axes. And then we're trying to investigate how it looks like. So what we usually do is we want to normalize our system. Okay? So remember, your f naught is f divided by m. And then you can move this divided by m in front. And then let's recall that k over m, that's just omega n squared. So eventually, what you can write, so that's your amplitude of your force. Eventually, we can write it as a ratio, F out over input force, F naught, generated by the person, equals to omega n squared over omega minus omega n squared plus 2 omega n omega zeta squared. So this is how much force applied by the person. And then on top, this is how much force experienced by the legs. Make sense? If your input force, according to these simplified cases, if your F naught is constant, we just want to minimize this ratio, right? Hopefully this ratio is minimized so that the force experienced by the legs will be minimized as well. Then what we can do is we can just plot this ratio as a function of omega, and then and then check how it looks like in practice. So I provide the MATLAB code, and you can actually see these in the lecture notes as well. It looks like something like this. So that's for small zeta. That's for zeta equals to 0.7. And this is for large zeta. So that's how the curve look like. So if you look at the curve, there are actually, I would say 2 or 3 cases. The first case is zeta small. In this case, you're going to see a peak in your response. And then we call this peak as resonance. All right, so let me go back to the lecture notes. I do have some equations over there. Yep. So this is F out over F naught. And then, as I said, there are 3 cases. That's FTR. So that's your case 1, when your zeta is small. So you're going to see a resonance in your system. So that means the location of these is when your omega equals to R peak times omega n. And then what is this R peak? Your R peak is related to damping. that's the location of your peak. So that means when you design your table, all the other frequency doesn't really matter. You just want to find the resonance and make sure your table survives the resonance. So up to 1 point, usually when zeta is greater than 0.7, that's a magic number here, then no resonance exists. So in this case, you just need to design for the static state, for the stationary state. You just make sure when the paper is on the table, it's not breaking. Then no matter how that guy jumps, it will never break. So that's when you really have really high damping in your system. That's the case. If you keep increase the damping, then this thing is just getting steeper and steeper. That's how you increase your damping or your damping ratio. So what does this tell us? It tells us like a few things. If it's for the table design, it says, okay, we actually need more damping in those legs. So we don't have to worry about the resonance. That's one thing. And the other thing is if we don't have enough damping, then we need to design the legs so that it can survive the peak. Okay, so any questions? All right, if no questions, then let me see. We have 15 minutes. We can move on.
Yeah, I was going to ask, can we go over like an example, kind of like a little more like one of the homeworks or something?
Yeah, let me see. Where is the, I'm trying to find a proper question for that. I don't think I have a very good, oh, I see. Actually, homework 2, I believe, that asks you to calculate the maximum steady response. So you can, I think we don't have enough time to cover these, but I'm going to post the solution online.
Okay,
right.
yeah, and I'll try attempting it, and we'll see how it goes.
Yeah, let's please do these after class. Perhaps at the beginning of next lecture, I can go over these. But I think it's a good time actually to review the Lagranges as well. Then I would like to make sure everyone have the same equation of motion to start with. So here we have a damped system, and then there is a joint here. There's a rigid bar. So actually that joint is not clear. So the bar should be, so these are rigid bar rotating around this joint. So if you want to use Lagrange's method to find the equation of motion, we talk about this. You want to find your L equals to T minus U. Your T is kinetic energy. So in this case, it's a single mass rotating around a joint. So you can define these angle as theta. So it's theta dot square. And then your J is a single mass around a point, so it's ml squared. So that's half ml squared theta dot squared. And then what's your potential energy? Let's assume the deflection here is x1. It's just half k x1 squared. There's no gravity. You can actually, no gravity. Okay, so remember that your x1 is just theta times L1. And you have a T, have a U, because we have damping. You also have to calculate the Rayleigh dissipation function. That's half of the C times x2 dot squared. So your x2 is the deflection of this damper or dashpot. So your x2 dot is theta dot L2 squared. And then we have a force. So that's why we have to calculate the K term. Your K is F vector dot product partial R partial theta. All right, so let's write out what this F is. Your F is minus Ft 0, because the horizontal component is to the negative and vertical component is just a 0. And then let's find out what the R vector is. As I said before, you have to find where the force is applied, where the origin is. You connect this. You have to shift this mass a little bit, otherwise your theta will be 0, so your relationship won't be clear. So your R vector is sine theta L minus cosine theta L. So your partial R partial theta becomes another vector, cosine theta L sine theta L. So once you know all of this, you can just follow the Lagrange's method, and I'm going to give you the final solution is ml squared theta double dot plus cl2 squared theta dot plus kl1 squared theta equals to minus ftl. So that's the solution for the first part, equation of motion. All right, then you can proceed to solve part 2 and part 3. And then I'm going to go over these at the beginning of the next lecture. All right. So any questions? If you have any questions related to project 1, you can also ask me right now.
I just have a quick question about this one. The MATLAB code for the 3-1, is that the generic solution that you were finding in there? Like initially with all of the, like it's symbolically that you had, like with all the variables in the first part? Is that
in lecture 3, so that's a most general live script. So in your project, I figured out that perhaps you don't have to be that general. Like I already give you those MCK values. You already know if it's underdamped or overdamped or critically damped. You just pick that condition that matches the actual problem.
Okay.
You don't have to solve for all 3 conditions. Just pick the one that works for you. If you don't like symbols, you can also substitute numbers in and then eventually your analytical expression will be in terms of numbers, not in terms of symbols. That's also okay.
Okay, cool. Thank you.
Mhm. All right, so if no questions, I think I will call for today. And I'm gonna post the lecture 8 homework solutions right now online. So if you're interested, if you can solve these homework too, and then want to check your answers, then you can do it. All right?
That's appreciated. Thank you, Professor.
Mm-hmm. Great.
You have a
See
wonderful
you.
weekend.
Yeah, you too.
Thanks.
Bye.